Thank you, Engineer Chidi, for your insightful presentation. It's good to know that WASA is building resiliency and redundancy into their system. Okay, ladies and gentlemen, we move forward. Before it is remiss of me, and I must say that we need to give due praise and thing of acknowledgement of our sponsors. The sponsor at our break we just had was Geotech Associates. We want to indicate from APET's point of view that we sincerely appreciate the sponsors who have made this event a success it is, and we look forward to your future partnering with us. Our next presentation is from engineer Dr. Arvind Singh, no relation, who gained his Bachelor of Science degree in Electrical and Computer Engineering at the University of the West Indies in 2003. Subsequently, he went on to study at the University of British Columbia, where he obtained his master's and doctoral degrees in 2006 and 2009, respectively. He is currently employed as a lecturer in energy systems at the University of the West Indies, where his research focuses on condition monitoring of power transformers and electrical machines, renewable energy, large-scale energy management systems, and power systems problems, peculiar to small island development states. He was instrumental in the recent formation of the IET Complex Interdependent Systems Community, focusing on analyzing the interdependencies between critical infrastructures and services in times of disaster. In addition to these, he was also involved in developing pedagogical tools for teaching of music and language. I welcome Engineer Singh to the podium.
Yes. Good morning, everyone. All protocols observed. Today, I'll be talking to you briefly about some research activities we have going on at the UWI in the Department of Electrical and Computer Engineering. So yesterday, I heard a statement by, I believe it was Engineer Gibbs, who was talking about one of these insurance companies that employs a lot of engineers. And he was saying that actuaries tell you what happened in the past, engineers tell you how you can effect change in the future. And the way that we engineers begin that effecting of change for the future is really through research. So what I'm going to take you through today is a brief overview of the department, one of the groups we formed within it, an informal group, and how this group has started to look at the problem of emergency management, disaster management, and so on, and a brief overview of some of the research that we have going on. Now, what I would like, and this is not a very detailed technical presentation, I really hope this would be the beginning of collaboration between different groups with the university so that we could create some meaningful research and meaningful way forward in the area. So, first of all, the Department of Electrical and Computer Engineering, our mission is to produce competent, bold, articulate engineering graduates and to conduct relevant and innovative research and development for the social, economic, and intellectual growth of the Caribbean region and beyond. And you'd notice we put competent before bold, because sometimes in this country, we have a tendency to go bold before competent. So we also, I have highlighted here one of the cores of what we are mandated to do, which is to conduct relevant and innovative research and development. Now, the department is broken up into 5 core groups: energy systems, control systems, communication systems, computer systems, and electronic systems. And some of the members of the department, we got together and we kept seeing, year after year after year, disaster after disaster after disaster in the Caribbean, the extreme toll it takes on the economy, especially tourist and agro-economies. I was surprised yesterday to hear the numbers, 180%, 200%, 300% of the GDP that single events can set you back. So we got together and we asked ourselves, well, how could we leverage the expertise in the department to aid in coping with these disasters? So from that, we formed what we call the Complex Interdependent Systems Collaboratory. And yes, collaboratory is a word. So it is comprised of 5 members, myself, we have Dr. Rochelle Adams in communications, Dr. Kim Malalu, Dr. Akash Puran Singh in computers, and Dr. Sean Rock also in communications. We have, although this is a new area for us, we have some linkages. We are linked with the Complex Systems Group in the University of British Columbia in Canada, and we're going to look at some of the work that they were involved in, and this is where I was also inducted into this, this type of research, disaster management research. We've just started actually some talks with the ODPM. This is still in the very incubatory stages, but we hope it carries on. And we have some linkages with the Trinidad and Tobago Coast Guard. Other linkages that we have, this is really just to show you that, we are not total ivory tower researchers. An industry has this, opinion of a lot of universities and academics that all we do is sit down and we theorize and we do some models and this sort of thing, and we don't ever put forward anything concrete. And yes, there may be some truth to that, but that is because that is not really the job of the university, and I'll talk a little bit more about that in coming up. Now, I don't know what all of these acronyms mean because they're from 5 different people. So the ones I could tell you, TNTech and PowerGen, which everyone knows, and MIT, which is, of course, the Massachusetts Institute of Technology. So while we're not on the ground, doing the work as a lot of you all are, and we don't have, the actual case studies to show, we're not completely in the dark. We actually do go out and work with industries and, see what is going on. So why did we call it the Complex Interdependent Systems Collaboratory? What are complex interdependent systems? Well, complex interdependent systems are networks of heterogeneous components that produce an emergent behavior. And emergent behavior is really behavior that is not predictable by looking at the constituent parts of the network. So the typical philosophical example of this is the clock. If you look at all the different gears in the clock, the hands, the face, all these things, you can't tell that the function this is going to perform or the behavior is to tell time. Right? So this that I have up here is Forrester's world system. And this was by a social scientist who decided he was going to model the entire world, all the processes, political, environmental, industrial, everything, and see how everything interconnects to each other. And you can see it's a very complex model. So what does all this have to do with disaster management and emergency response? Well, emergency response is a complex problem. We have a lot of different infrastructures. We have the transportation system, the electrical system, the water system, sanitation systems. We have ports, we have roads, and all of these things interact to give us a mode of living, to give us day-to-day life, in which they are transparent. We don't think about them. We assume everything is working. So when you look at TV, you're not looking at the communication system and the electrical system. You're simply seeing the content being streamed to you. So it is not immediately obvious how all these things connect together to work. But when a disaster hits, what happens? We suddenly have a shortfall of resources. We have an absence of services. So the problem then is, how do we manage these limited resources in order to quickly bring back the system or to get the least amount of losses in the system? So this is sort of how we started looking at the problem. And we looked at the phases of emergency management, and we tried to decide where could we fit in. Now, these are very general categories. Of course, we're not going to go into all the activities involved in preparation and response and so on. So very generally, we looked at preparation, which is you're doing your planning, your training, you're doing capacity building, And this is really a continuous process. Even when the disaster hits, you're collecting data that is going to help you in the future. So all of these are part of within the disaster itself, you are still preparing for the next one through these data collection exercises. We have the response period, where we have things like search and rescue, setting up of triage and shelters, provision of basic necessities, and so on. And this is in a time span of minutes to days. And then we have the recovery period. And what is the difference between the response and the recovery? I think it goes to some of these psychosocial factors that I don't know if it's engineer Dr. Ramrup, since he's an orthopedic surgeon. So this goes to some of those psychosocial factors. So when that liminality created by the disaster, where everything is up in the air, nothing is certain, what is going on in the mind of the population, and when does the population move to a state of acceptance and so on, so that the rebuilding process can take place. Right now, we see ourselves primarily in the first two, but of course, in future, we could move on to also aiding in the recovery process. So, how do we fit into the preparation process? Preliminarily, or primarily, I should say, in technology, we have things like DTV standards harmonization. We are looking also at multimodal, multi-agent, multi-dimensional ICT engagement and participatory platforms. I'll show you what I mean by that coming up. And we're looking at critical infrastructure interdependencies. How do we understand how all the different infrastructures interact in order to understand what impact our decisions have? If we decide allocate this amount of resources here instead of here, what does that mean in the final analysis of the system? So that is what we're doing in preparation time. In response time, again, we're looking at communications networks, setting up ad hoc networks, which are much more important in disaster times as opposed to having centralized communication systems, which, they have geographic fixity and so on. So if they go down, well, you've lost a significant part of your infrastructure. And looking at communicating with the general population, doing coordination and information sharing, and I believe, was it Engineer Williams yesterday from TSCT? I don't know if I got his name correct. He was talking about the importance of data in the aftermath of the disaster. So those are some of the things that we are looking at. So to get into the research now, understanding critical interdependencies between infrastructures. This was a project that was started in the University of British Columbia, Vancouver, in about 2005. And I was there since the inception, helping them develop the models and so on. So when I came down here, I brought it with me. And you'll see the subcaption there, I2SIM. What I2SIM means is infrastructure interdependencies simulator. And some of you would have seen Professor Marty in our IEEE presentation. It's sometime in the middle of last year, doing a very detailed presentation on it and its uses. Now, the basis of the simulator is that when we have these complex systems, these complex interdependent infrastructures, how do we know what our decisions are going to do? Usually, human beings, we think in very linear pathways. So we say, if I do this, this translates directly into a shortfall of that and that and that. This is fine if you have a linear sort of setup in your infrastructure connections, but we don't. Everything is interconnected. So how do we know when we make a decision what is going to happen? It is not as simple as just tracking the shortfall of resources from one place to the next. So this is what the simulator tries to accomplish. And why don't we just say, well, this is a disaster, just assume you have nothing and make and build your plan around that, because then obviously you don't need to depend on anyone else. Well, that is good, but if you take this sort of binary resource view, you could end up with stockpiling of resources. You could end up with a very inefficient use of your resources. So I2SIM is a tool which could help us to understand how these decisions play out by doing simulations. And it is useful for vulnerability analysis. And here, I don't mean structural vulnerability analysis, I mean system vulnerability analysis in terms of resource distribution and so on. We can identify what are critical points in the system that need reinforcement, and we can balance cost and risk by understanding what is the sensitivity of the system to different parameters. At its heart, it is really an ontology that could be used to unify a set of different systems that each have their own language and bring them into a common platform. So you have water, you have electricity, you have all these things, and everyone has their own simulator. You have in the communication system, detailed communication simulations, you have detailed electrical system simulations, but they don't talk to each other. They all assume that they're working independently. I2Sim is a platform that will take all of them and put them together in a common arena. So what does the simulator actually do? I'll go through a really, really simple example. And it is actually so simple that it is not really realistic. But if we get any more complex than that, it'll be very difficult to see what the concept is. So just imagine we have some electricity provider, and it's providing to some group of hospitals and some water stations. So the hospital needs both these things to operate. And now you have an event that causes some of the electrical power to go down. How do you allocate power? Where do you send the power? Right? The electricity system will have their own priority tables. But these are more often than not, and maybe I'm wrong, developed in isolation. So they're looking at who they believe their most important customers are. And again, this is a very binary way to do things. So how do we distribute this power now? Well, you might have many different ideas of what we could do. We could continue doing things as we always have. We could shut off the water and deliver to the hospital. We could shut off the hospital and deliver to the water system. So using I2Sim, what we could do is we could simulate the decisions and see what is the net effect on the system. Now, this is a very simple system. What happens if we have a more complex system? You might say, well, oh, water, electricity, that is, we could very easily do that. But what if we have a more complex system? This is some work that we did at UBC for Defense Research and Development Canada for the 2010 Olympics, where we looked at egress of stadia and so on in the case of disasters. So you can see they're not just 3 cells. We have 4148 and 210. Or we could look at something like the island of Guadeloupe, where we model 59 cells, 349 channels, and 100 control points. And this was done at UBC for Matrix, which is a European Union project looking at multi-hazard propagation as well as how we manage the disasters. So I2Sim came after the multi-hazard part. So you look at the propagation of the disaster itself, and then we look at how we manage the disaster afterwards. So these are just some examples of the models that we could use, and we could tell things like if we have a shortfall of power, just to give you some examples. In Sendai, when there was that shortfall of power, and you have to have a rotating blackout, what do you take into consideration? Are you just doing very standard time slots, 8 hours, 8 hours, 8 hours, and you black out communities in turn? Or are you going to look at the demographics and say certain areas have elderly populations that are more prone to going to the hospital if they lose heat, and then leave them on for longer periods of time? These are the types of studies that we could do. So we also have some things in disaster effective communications that was done by engineer Shiva Kisoon, who's sitting right there for his MASc thesis, where we looked at things like the success rates for different communication technologies under different conditions and so on, how many times you have to retry. This again can tell you how much emphasis to place on different technologies, where to put your money in reinforcing your system. So that was one area of research. We have another area of research, mobile ICT platforms. And you can see this is an actual device that was developed, well, not a device, but an application platform that was developed for fishermen. One of the applications there is an SOS platform. This has been deployed already. And really, the mobile phone is a sensor. And if data is important, then having crowdsourced information from the general population means you have a huge dendritic web of sensors that could really improve your ability to make decisions and your ability to manage the disasters. And of course, you're probably thinking, well, all that is fine, but if you have to have that sort of capability, then you need a communication system to support it. How do you know the communication system is going to be there? So another thing we're looking at is ICTs for these emergency communications, ad hoc DTV networks. So the Caribbean has to switch over to DTV by 2015 or 2016. This will free up a lot of bandwidth and allow a lot more users on the channels. So could we co-opt some of those channels specifically for emergency communications? And the technology that we are developing, well, one of my colleagues is developing, is software-defined radio, where it could interact with any standards. It could be self-powered, just like ham radio, except at a much higher bandwidth. So you could get a lot more meaningful data types. You could stream video, you could have access to the internet, all of these things by powering a simple device. You could power it from a car, battery, anything. They're ad hoc. They don't require centralized infrastructure. So, as I said in the beginning, all of this was really to give you some idea of how we could collaborate. And I'll just give you, in closing, some avenues for collaboration. We have various student projects at different levels, even for the regional corporations and so on. We have student projects that you could get them to deploy early warning systems, simple monitoring systems, and so on. And it goes all the way up to PhD projects where you could do very detailed long-term studies. We can have internships if you want for the ODPM and so on, if you want somebody more permanent, somebody that could look at your context more specifically. And for development, product development and innovation, that is something that begins at the university, but it doesn't end at the university. So this is why we're talking about startup companies and so on. The university is not a commercial house. So the ideas could begin here, but eventually they can be taken and commercialized by different startup companies. So that is basically it. I think there is a lot of room for collaboration between all of us, and we look forward to really interacting with the community and anybody who is interested in collaborating. Thanks.